some fairly in-depth problems here in chapter 11, so I think it's worthwhile going through and practicing a few more examples just to make sure we're kind of clear on all the things that we might encounter as we move on to some of the sort of testing type materials. So the first problem here, we've got this compound, anthracene. We're given the empirical formula of the compound. We want to figure out its molecular formula, so we use colligative properties. We dissolve a sample, we know the mass of it, in a certain amount of solvent, and then we compare the, so the pure benzene boils at 80.10, the solution we made boils at 80.34. We want to figure out what the molecular formula of anthracene is. So to get to the molecular formula, we're going to need the molar mass. So we want to get to the molar mass. We want to start here. The boiling point. Now, once we have delta T for the boiling point, we already have the constant up here. For boiling point, so that molality is on one side, so I just divided through by the constant. In this case, we can take our change in temperature, divide by our constant, and that will give us the molality of this solution. So 0.24 divided by 2.65 is 0.0906 molals for this particular solution. Okay, now again, just like we saw in one of the previous examples, that's molality. That is not necessarily moles, because that's dependent on how much solvent was in the system. So if I take that value and go back over to the left side here, but now I extend those units or expand those units. This is moles of my anthracene relative to how many kilograms of solvent were used to make that solution. So I can get to how many moles of my unknown material there are if I multiply by how many kilograms of solvent were used. Now, solvent up here is in grams. Of course, there's 1,000 grams in a kilogram, so I move the decimal 3 places. That would be how many kilograms there are. So 0.030 kilograms of solvent were used. This will cancel out kilograms and leave me with how many moles of this unknown anthracene there are. So times 0.03, and this would be 2.717 times 10 to the minus third moles of anthracene. Now, we know how many moles there are. We also know how much anthracene we had to begin with, so we have both of the pieces to calculate the molar mass. So the molar mass of this unknown, we take the mass of the sample we used, 0.5 grams, divide by the number of moles that we just determined from the colligative properties, and that would give us the molar mass, grams per mole. So 0.5 divided by 0.717 times 10 to the minus third. That comes out to be 184 grams per mole. Now, if you look back at our temperature change, it's only two significant figures, so we should maybe call this 180 grams per mole instead, without a decimal. Although in this case, that's not really our final answer to the problem. What we're really asked for is what is the molecular formula of anthracene. So kind of think all the way back to the beginning of Chem 1, we learned how to relate the empirical formula to the molar mass to figure out what the molecular formula is. So 180 here is our molar mass. Let me write it out here. The molar mass is 180. what we want to do is figure out what is the mass of the empirical formula, because the mass of the empirical formula has to be related to the mass of the entire formula. So for the empirical formula, if we take 7 carbons, 5 hydrogens, right, 7 times 12 is 84. Hydrogen is 1, so 5. That would be 89. Now I'm leaving off the decimals here because we're just looking for the integer that relates the empirical formula to the molar mass or to the molecular formula. So if I take my molar mass, 180, and I divide by my empirical mass, 189, that should give me the size ratio between the empirical formula and the molecular formula. You can see that's going to be very close to 2.02. And so that means the molar mass is twice the empirical mass. So the formula for the molecule itself is going to be twice the empirical formula for the compound. So if I take C7H5, multiply through by 2, that would be C14H10. That is my molecular formula for anthracene. So a little kind of throwback to some earlier calculations there. Primarily, you should be more focused on being able to calculate the molar mass. But it is always fun to tie in those older calculations that you have such fond memories of from your earlier chemistry experiences. Okay, second problem. The freezing point of a solution made by dissolving 1 mole of hydrogen fluoride, that's HF, in 500 grams of water is minus 3.8 degrees C. Freezing point of a solution prepared by dissolving 1 mole of hydrogen chloride, HCl, in 500 grams of water is minus 7.4 degrees C. And we're asked to explain that. So, a couple things here. We have the same amount of solvent. We know that the constants in this case for freezing point depression are based on the solvent, so it would be the same constant in each case. We also have the same quantity, 1 mole, of each of the 2 components. So the molalities of these solutions would be the same, the constants would be the same. The only factor that could cause the temperatures to be different is going to be related to how many particles are in that solution. So since HCl is giving us a bigger temperature change here, HCl must be producing more particles. So when we dissolve HCl in water, it must be making more particles. And in fact, what happens when HCl is dissolved in water is primarily it splits apart into H plus and Cl minus. So it's pretty much making 2 pieces when we put it in the solution. Now, the fact that HF has a much lower number, in fact, it's close to half, right? It's just a little more than half of what the value for HCl is. HF must not be making more particles. So HF doesn't break into particles. And that's mostly true. We'll actually see in a couple chapters, HF is what we would call a weak acid. When it's dissolved in water, it doesn't completely break apart. It's actually a 2-way reaction called an equilibrium reaction that we haven't talked about yet. Most of the HF stays as HF connected together. Just a little bit breaks apart. But that kind of gets a little more complicated, but that's something we'll come back to. But in this particular case, that's the only possible explanation, is a Van Hoff factor type explanation, how many particles are being produced in the solution.